So, good afternoon, welcome. My topic today is modern Java in an era where change is the only constant. In the past 2 years, we changed the Java platform in 3 ways that we never have before. We took this massive monolithic platform that had grown monotonically over time and sliced it up into 26 standard modules. Second, we removed the Java EE and Corba modules and some other APIs, leaving us with 19 standard modules. And third, we left behind our historically grand and majestic but slow-moving and unpredictable release model, in which we shipped a major release every 2 to 5 or even 7 years. We replaced it with a rapid cadence release model, in which we ship a feature release every 6 months on a strict time-based schedule. Now, modularizing the platform and removing some modules did break a few things. Many have wondered whether the Java ecosystem as a whole will be able to keep up with a 6-month cadence. Taken together, all of these changes are, well, frankly, somewhat scary, but maybe not as scary as you think. Why did we make them? Because adapt or perish now as ever is nature's inexorable imperative, according to H.G. Wells. Or, if you prefer a more modern formulation, adapt or die. So saith Andy Grove. We must change Java in new ways because its competitive environment is very different than it was 20 years ago. There have been 2 big, broad changes. First, many popular platforms now ship new features around once a year, if not every 6 months. If Java is to remain competitive, we must move the platform forward faster. Second, applications are packaged and deployed in different ways than they were 20 years ago. Whether it's the cloud or in packaged apps that are published in app stores, if Java is to remain competitive, we must adapt it to these new environments. Let's look at the first big change, modularizing the platform. This is where we ended up. Nice, clean module graph with 26 standard modules. The base module at the bottom, that's the one module you always need. It's got Java Lang string, Java Lang object in it. The JDK has these standard modules plus many more non-standard modules that contain development and debugging tools, service providers, and various JDK-specific APIs. This pretty picture is not where we started. Where we started was here. A spaghetti bowl of tightly coupled platform components with sometimes surprising interconnections. To print Hello World, you needed Corba. Slicing all this up while maintaining as much compatibility as possible took years of painstaking refactoring and delicate surgery. We were finally able to deliver on that in JDK 9. Now, modularizing an old code base can be a ton of work, but modularizing the platform yielded many benefits. One benefit is that it's more flexible. A module names the modules upon which it depends, so the compiler and the runtime system can ensure the reliable configuration of consistent subsets of the platform. Most applications, after all, don't need all of these modules. If you have an app that only uses the SQL module and the base module, then you can link a custom runtime system that contains just those 2 modules, plus any other modules that they need. The rest of the modules simply fall away. You can package this custom runtime system with your app, resulting in smaller Docker images, smaller App Store packages on the order of tens of megabytes rather than hundreds. To take advantage of this, you don't need to modularize your app. You can do that if you want, and there are many good reasons to do so, but it can be an awful lot of work, and if your app is essentially in maintenance mode, it's probably not worth it. Another benefit of the modular platform is that it's more secure. A module exports the specific packages for use only by the modules that depend upon it, so the compiler and the runtime system can enforce strong encapsulation. How much more secure is it? Of the 6 high-impact zero-day vulnerabilities reported since JDK 7 in 2011, 3 of them would have been prevented if we'd been able to strongly encapsulate the JDK's internal APIs. A final benefit of the modular platform is that it's easier to maintain. The JDK does indeed have many internal APIs, never meant to be used by external code. For decades, we've been warning developers, don't use these. Please don't use these. They've done that anyway, of course, sometimes in some disturbingly popular libraries. Now, to be fair, in some cases, they were after critical functionality that they could get in no other way. So, okay, fair play, fine. But in many cases, frankly, they were just lazy, as we all can be. Why write your own base64 encoder when there's a perfectly good one sitting over in the SunMISC package? Totally unsupported, but it's there. Because of this, for 20 years, we've treated many internal APIs as if they were standard. We've been reluctant to change them because we don't want to break people's code. This has, however, made the platform harder to maintain and harder to evolve. With strong encapsulation, we can close off all access to the internal APIs of the JDK simply by not exporting the packages that contain them. If we did that right away, we would definitely break a lot of existing code. So we're taking a more gradual, nuanced approach, since migration takes time, especially in such a large ecosystem. Starting with JDK 9, and at least through JDK 11, if your code uses JDK internal APIs, then it will not compile, and it may generate warnings at runtime. And by your code here, I mean not just the code that you write yourself, but all those libraries that you pulled down from Maven Central. We have deliberately relaxed the strong encapsulation of legacy JDK internal packages for now at runtime so that old code continues to run. We will eventually strengthen the encapsulation of these packages once we've provided standard APIs for the critical internal APIs and once everyone has had a chance to fix their old code. When we do that in some future release, not very far off, code that uses JDK internal APIs will not run. In the meantime, here's an example of the kind of warning you might see if you haven't seen one of these already. This is the console output of Jython, a Python interpreter written in Java running on JDK 9. Several warning lines here to interpret. First, an illegal reflective access operation has occurred. This is one that will be impossible at some point in the future. The warning identifies the code responsible, and it also shows the internal API that was accessed. It helpfully suggests that you report this error to the maintainers of the errant library so you can do your part to help push the ecosystem forward. It tells you how to get additional warnings if you want to see them, because by default, only the first one of these warnings will be shown. You don't want to mess up your output too much, just a bit, just enough to be annoying. And finally, it reminds you that all illegal access operations will be denied in a future release. To help you get ready for that future when such code will not run, we introduced a new tool in JDK 9 called JDEPS. If you run it against an existing jar file with the --JDK internals option, it can detect most uses of internal APIs. As an example, here it detected the use of sun.security.x509.x500 name, which is indeed a JDK internal API, and it even suggested a standard replacement. You read carefully, that standard replacement has been there since Java 1.4, which was released in 2002. There's really no excuse not to be using it. So the modular platform does break some things, but it doesn't break everything. In fact, if your code uses only standard Java SE APIs, then it most likely will work without change. I say most likely here because there are yet some very minor differences. We removed a few obscure, rarely used methods and mechanisms to enable the clean modularization of the platform. We also made some behavioral changes that honor the specification, but in rare cases might break existing code. If you want to know more, have a look at JEPS 261, which lays out all of the compatibility-related changes in great detail. Beyond that, to learn more about Java modules and the modular platform, I can recommend all three of these excellent books. The modular platform enabled the second big change of the past year. We've reduced the platform by actually removing things for the first time in Java's history, or at least, well, the first time on purpose. We removed the Java EE and Corba modules in Java 11. Poof, they're gone. Why did we do this? Well, The details are all in JEP 320, but in a nutshell, these are costly to maintain. They've been the source of multiple security vulnerabilities over the years, and nowadays they're either available elsewhere, as in the case of Java EE, or they're just no longer relevant, as in the case of Corba. We removed some other smaller things too. As I mentioned, in order to modularize the platform cleanly, we removed some fairly obscure methods in Java 9. Most of these are for configuring property change listeners in various core APIs. Frankly, they probably never should have been added in the first place, but there they were. We only removed these after analyzing lots of code out in the wild to see if anyone was using them, which hardly anyone was. While we were at it, we also removed a pointless constructor that had somehow, Brian, snuck into Java 8. We removed more methods in Java 10. All of these methods are ill-defined, actively harmful, don't work, or don't do anything useful. We removed yet more such methods and one class in Java 11. Now, removing things, yes, it can cause breakage. So to ease the pain, we always give advance notice by deprecating APIs to be removed at least one release in advance, if not more. As an example of that advance notice, here are all the APIs deprecated in Java 11 for removal in a future release. If you look carefully, you can see that these include many finalize methods sprinkled through the core APIs. We're removing those because finalization is a fundamentally broken mechanism that we have finally replaced with something better. Now, when an API is deprecated for removal, that's always noted in its Java doc. For example, here is a method named trace method calls in the Java-lang runtime class. This dates way back to before Java 1.0, when all we had were bytecode interpreters. This was an API designed to let you control tracing of method tracing of a bytecode interpreter. As you can see, it says this method was intended to control method call tracing. It has been superseded by JVM-specific tracing mechanisms, also known as JVM-TI. Note the subtle and sophisticated specification, not implemented, does nothing. Few people will miss this method, I suspect. If you compile source code that uses an API that's deprecated for removal, then, of course, the compiler will helpfully warn you about it. OK, popping up a level. First, we modularized the platform. Then we trimmed it down. And then we started moving it forward at a faster pace with a new release every 6 months. How can that possibly work, you might be thinking? Well, let's look at a timeline. We shipped JDK 9 in September 2017. We shipped JDK 10 just over a year ago. We shipped 11 last September, and we'll ship 12 next month, and so on every 6 months, like clockwork. A feature release can contain any kind of feature, a language feature, a library feature, a performance feature, a JVM feature. It can even contain a feature that removes an old feature. For this to work, a feature can go in only when it's nearly finished, because we can no longer slip a release in order to fix a broken feature. But if a feature misses the current release, that's OK. The next one is only 6 months away. It's not 3 years or 5 years or 7 years in the worst case. At the beginning of all this, of course, was JDK 9, the final massive JDK release. It contained 90 JEPs, 90 major features. We shipped it 3 years and 6 months after JDK 8, which had shipped in 2014. We did that with 2 major slips to the schedule. Now, engineers from Oracle did much of the work shown here, but not all of it. 6 JEPs came from outside Oracle by contributors from Red Hat, Linaro, and SAP, plus a couple of independent folks, Doug Lee and Laurent Borges. These non-Oracle contributions included 3 whole CPU ports, some significant performance work, and a brand new 2D graphics rasterizer. So after all this, and of course, Jigsaw, the module system was in here too. After all this, what was going to be in JDK 10? One worry that we actually had about the 6-month cadence was we might wind up with 0 features in a release. I mean, if nothing's ready, well, the release is going to ship, and well, maybe it's just a bunch of bug fixes and small enhancements. It's theoretically possible for there to be no major features. Happily, that turned out not to be the case. JDK 10 contained 12 JEPs, including 1 language feature, local variable type inference, more performance work, a massive refactoring of the source code into a single Mercurial repository. And again, Oracle engineers did much of the work, but not all of it. 2 JEPs came from other contributors. Roman Kenke of Red Hat contributed a GC interface, and some engineers from Intel enabled heap allocation on alternative memory devices. This pattern continued with JDK 11 last September. There were 17 JEPs in JDK 11, including some long-needed JVM improvements, a brand new HTTP client API, the ability to launch single-file source code programs, which is really handy for quick debugging, and TLS 1.3, just in time for the final internet standard. Oracle engineers did, again, do most of this work, but 3 JEPs were contributed by others. Engineers from Bellsoft and Cavium contributed work on ARM64 performance. Alexei Shibulev of Red Hat contributed the Epsilon garbage collector, a garbage collector that never collects, which is actually useful for some things. And Jean-Christophe Byler of Google contributed low overhead heap profiling. Finally, that brings us to JDK 12. Still in development, the first release candidate build will hopefully be tomorrow, this week, tomorrow, Thursday. There are 8 JEPs in JDK 12, including a micro benchmark suite for the JDK itself, a preview language feature, switch expressions, and various VM performance improvements. Again, Oracle engineers did most of this work, but in JDK 12, we do have an entire new garbage collector, Shenandoah, contributed by Christine Flood, Roman Kenke, Alexei Shibulev, and others at Red Hat. If you'd like to test out JDK 12, especially once we have the release candidate build, hopefully tomorrow, you can get it here, download it, test it. If you find something wrong, please let us know as soon as you can. So as you can see, what has changed is not the rate of innovation. We continue to innovate at a regular pace. What's changed is the rate of innovation delivery. We can now deliver every 6 months. In 3 years, by 2021 or so, we probably will have merged around 90 JEPs, just as we had in JDK 9. These feature releases aren't just about JEPs, of course. Each contains many smaller enhancements and, of course, bug fixes. As an example, according to our bug database, in JDK 11, we resolved almost 2,500 issues. Oracle engineers were responsible for most of these, but there were significant contributions from engineers at SAP, Red Hat, Google, Bellsoft, and a smattering of very productive individuals. Returning to our timeline, the 6-month cadence will enable Java to compete better with other platforms, but you might be wondering, what about updates, security fixes, critical patches? The plan in the OpenJDK community is to update the current feature released for at least 6 months. That is 2 quarterly update releases. And then every 3 years, we'll declare a long-term support release. JDK 11, shipped this past September, is the first long-term support release. The next will be 17 in 2021. If you like, you can imagine JDK 8 way up there to the left as the previous long-term support release. Each of these LTS releases will be updated well past the beginning of the next LTS release, and possibly even longer. Now, you might think that LTS releases are in some way experimental. Oh, they're just fancy beta releases, but they're not. Every release is production ready. What differs is only the support timeline. So, you have a new kind of choice to make. You can take the blue pill or the red pill. You take the blue pill, you wake up in your bed and continue to develop and deploy uncomfortable, conservatively managed, slow-moving LTS releases with an update release every quarter and a major migration every 3 years. You take the red pill, you go down the rabbit hole, where you can enjoy the latest language features, API enhancements, performance improvements, and bug fixes with a minor migration every 6 months. It's up to you. All I offer is the truth. If you do choose the LTS path and take the blue pill, you might be wondering, who will produce your update releases? Again, you have a choice to make. Since JDK 9, Oracle contributors in the OpenJDK community have focused and will continue to focus primarily on feature releases rather than on updates. Oracle will ship OpenJDK builds under the GPL for the first 6 months of each feature release. That's the GA release plus 2 updates, whether the release is a long-term support release or not. After that, Oracle will offer long-term support builds, but in a change from the past, these will be available only under a commercial license that allows free use for development and testing, but requires payment for use in production. That might sound scary, but don't worry. Java is still free. All of the code is still available under the GPL for anyone to build, test, publish, update, and support. Oracle engineers won't regularly contribute to, or much less lead, LTS releases as they have in the past. That's okay. The OpenJDK community as a whole has a proven track record of transitioning the leadership of update releases from Oracle engineers to non-Oracle engineers. We did that years ago for JDK 6 and JDK 7. We did it again for JDK 8 just last week when Andrew Haley of Red Hat took on the leadership of the JDK 8 updates project. We're already in the process of doing the same for JDK 11. This isn't just my personal fantasy. As Andrew Haley has assured everyone, whether by Oracle or Red Hat or someone else, JDK LTS releases will continue to be supported. We all have a lot invested in Java, and we won't let it fall. So the LTS work will carry on in the OpenJDK community as it has in the past. You'll be able to get carefully built, well-tested JDK LTS builds based upon all that source code in most any Linux distribution, whether it's derived from Red Hat Debian, Gentoo, or Arch. If you're not on Linux, you'll be able to get LTS builds for free from a variety of providers. For this plan to work, it's critical that you be able to switch from one provider to another. In past releases, that wasn't possible because Oracle always held back a few so-called commercial features that were available only to paying customers. These included application class data sharing, Java Flight Recorder, Java Mission Control, and the Z garbage collector. To enable such switching and to establish a level playing field across all providers over the past year, Oracle open-sourced all of these commercial features so that Oracle builds and OpenJDK builds are functionally interchangeable at this point. You can switch from one provider to another as you please. But when you choose a provider, you might want to consider those with the depth of knowledge that comes only from a long-term investment in the platform. You have a choice. You can take the blue pill or the red pill. You can choose the conservative LTS path and take the blue pill with a major migration every 3 years. This can be a fine and appropriate choice for conventional enterprise-style deployments of large applications on large servers. Or you can choose the aggressive feature release path and take the red pill with a small migration every 6 months. This can be a good choice if you're deploying to the cloud or to app stores. If you choose the LTS path and take the blue pill, then you shouldn't ignore the non-LTS releases. Some free advice. If you maintain an infrequently migrated system, then you should still test it with each non-LTS release. That way you'll be nearly ready for the next LTS release by the time it's available. You will have spread out the migration work over time. If, on the other hand, you choose the adventurous feature release path and take the red pill, then you're going to migrate to each feature release as it becomes available every 6 months. So make sure that your tools and dependencies can keep up. Many will be able to keep up, but some won't, especially if they're no longer maintained. So plan with care. To sum up, we are evolving the Java platform at a faster pace. We're doing this in order to keep up with competing platforms. We have broken a few things and will continue to do so in order to make Java a better fit for modern applications. Are these changes really all that scary? No, I don't think they are, for 4 main reasons. One is that we will always give advance notice before removing anything, and we'll only do so when there's a very good reason. We don't want to break existing code unnecessarily, because compatibility remains one of the core values of the Java platform. Second, you have a choice to make, which you didn't have before. You can take the blue pill and migrate every 3 years at a comfortable, stately pace, or you can take the red pill and enjoy the latest features and fixes every 6 months. It's up to you. Third, it's true that Oracle will no longer provide free long-term JDK updates, but Java is still free. Free updates will be available from a variety of other providers, including all of the major Linux distributions. If you want active support, someone you can call when something goes wrong, then you're probably going to have to pay someone or else do it yourself. But that's always been the case. So choose your provider wisely. Finally, we did break a few things. Migrating past Java 8 may require some work, but it might not be as hard as you think. All 3 of the major IDEs already support essentially all of the new language features. Many popular tools, libraries, and frameworks already support JDK 9, if not JDK 11, or even JDK 12. you don't have to take my word on this. As you might recall from last year, just after Java 9 was released, I asked on Twitter, do you maintain a popular Java library, framework, or tool? If it works fine on JDK 9, then please reply with its name and version. That, of course, was a year ago, well, a year and a half ago now. So shortly after JDK 11 was released, this past September, I asked, do you maintain a popular Java library, framework, or tool? If it works like heaven on JDK 11, then please reply with its name and version. My thanks to Sam Brannon of the JUnit team for that hashtag. There were many, many responses to these tweets. All 93 of these libraries, frameworks, and tools work just fine on JDK 9. They either worked without change, or in some cases their maintainers had to fix them, and in many of those cases the fixes they had to make were pretty straightforward. These include the build tools, Ant, Maven, and Gradle, test frameworks, JUnit, TestNG, popular libraries, ByteBuddy, Jackson, Log4j, Hibernate, Juke, Netty, and the entire Spring framework is in there. 51 of these components work not just fine on JDK 9, but like heaven on JDK 11. Since the transition from 9 to 11 is much easier than the transition from 8 to 9, I expect that the rest of them will catch up in short order. My most urgent advice to you today then is this. If you're using Java 9 or later, upgrade to the latest versions of all your tools and dependencies, because everything changes and nothing stands still. Don't believe a word I've said. Thank you very much.